Hello everyone, welcome back to ECE410 Power Electronics, class number 6, part number 2. In last part, we discussed about some DC-DC conversion, and we have seen that they have some very serious disadvantage in terms of efficiency. To overcome that, we need to go into switching DC-DC converter, right? Switching DC converter, if we can find the ideal switch, that could be 100% efficient. But in our analysis, we're going to talk about ideal switch, but in practice, there is no ideal switches. So there'll be some losses, but not as much as we have seen in the traditional non-switching DC-DC converter, all right? Let's get to a simple DC converter, 2x2 matrix. That could be input voltage, output current, because you know that you cannot connect like voltage to voltage or current to current. Voltage to voltage in parallel, because of dissimilar voltage creates a KBL violation. All right. So if you current in, your voltage out. So we're gonna do both of them. First one would be voltage in, current out. Second would be current in, voltage out. Let's talk about that. For this one over here, this is a buck converter. If you look at that, we're doing voltage to current conversion, voltage in, current out, right? And we also need reference to make sure that we have a reference on here. So we're gonna make this one permanently on, closed. So that means I cannot turn on this one. This is useless now. So I have only two switches right here, this one and this one, right? When one is on, your current coming in and going into the output, right? So then when 1 is on, you're basically circulating current in the output, right? So that let me show you what I'm talking about here. So when 1 is on, you're coming this way and going that and circulating back to the here, right? And when your 1 is on, that means you're circulating, 1 is on, you're circulating right here. You're circulating right there, right? So to visualize that, there's one more step over here, so that this is permanently closed. So I don't need this one anymore. I cannot do that because I'll violate the KVL. So I have to deal with these two. And when this one is on, as I said, you're gonna go from input to output current. So this one is on, so input to output right here, right? And when this one is on, this one is on here, so you're gonna circulate in here. That's right here. So I need to control these two switches, right? And input is voltage, output is current. So if you have an inductor at the output connected, so you can use a temporary current source for the output. So this inductor over here, this combination over here will use as a temporary current source, because you cannot change the current in the inductor instantaneously, right? So that means the input is voltage, output is current source. All right. So to do that, to find the relation between input and output, we can go back to our analysis we did before, which is your energy conservation analysis. So let's say your D ratio is D, so it would be V, L, I, L, dt. We're looking into current energy conservation across the inductor, plus dt to t is the period, and it would be VL, IL, dt, right? Should be equal to 0, right? So VL is the voltage across the inductor. When switch 1 is on, when switch this one is on over here, you can see that this inductor will have the voltage, which is difference between input voltage and output voltage, right? So over here, dt, VL would be V in minus V out. We have done it before, IL dt, right? And you remember that your inductor current cannot be changed instantaneously. We're gonna call it constant current. That's how you're using this part as a current source. All right, plus dt to t over here. Now when switch 2 is on, this one is on, so this is a loop here, right? Current is looping here, so your VL would be negative V out. So now that means this is negative V out here, IL dt should be equal to 0. Oops, sorry. Should be equal to 0. So if you finish this integration and some algebra over here, you should get V out equal to D times V in, right? You should get that equation right there. V out is V D times V in. Now, you can see over here that only time your input is connected to output when this switch is on. So that means on only that time your power transfer is happening from input to output. So output voltage should be a average value of how much this switch is on. So if I use that in other analysis over here, so V out is depends on how much your Q1 or switch 1 is on. So average time this Q1 on, that will give the average voltage at the output. So average voltage at the output is the average time Q1 is on, which is D1 times V in. So, and that is the relationship we just found out with the energy conservation theory, and also that applies to I in, average I in should be equal to D in times D1 times I out. For our normal operation, I always do D1 equal to D. That's your D ratio of switch 1. Right? Then you can find the P out and P in, that should be equal to each other. That means D1 V in I out would be output or input power. Right? So now over here, if you look at here, carrying current, so this one should carry output current. So your inductor should be rated for the output current, right? And this one here, this switch should be here. When this one is off, so your whole input voltage come across that switch. So that switch will be rated for input voltage. And also rated the current, input current goes through that switch, which that should also rated for input current. So that switch 1 should be rated for input voltage and input current. And this one over here should be rated for output current and output voltage, because output current goes through it. Look at here, when it's on, it circulates through that. And also output voltage comes across it when that one is off, right? So that is the rating blocking for the this one, when this one is off, that input voltage comes across it actually. So both switches will be rated for input voltage, and diode should be rated for output current, and switch 1, which is transistor, should be rated for input current, and your inductor should be rated for output current also. All right, so over here is I out, right? Capacitor should be also V out, output voltage comes across the capacitor. Diode should be V in and I out, right? Transistor is also V in and I in. So that's the rating for all those devices. We're going to talk about this in the class. What is the RMS value of a pulse, right? And I'm going to do this example in the class, so we can spend some time on it. And we're going to also do this. Now, boost converter. For the boost converter, we're basically connecting input current source to the output voltage source. And why is that? For boost converter, if you remember from the last chapter, this is the boost converter right here. Let me draw it. So this is the output over here. So output is constant voltage because across the capacitor, and this is the input voltage here. So this one here will act as a current source because of the inductor. Inductor keep the current constant, and that is right here. So you're connecting input current to the input current source to the output voltage source, right? So we're not violating KVL. And again, the switches are complementary. So Q1 plus Q2 equal to 1, because one switch should be on at a time. So over here, if I now convert this one to the equation over here, so V out, right? V out and V in. So V in over here, look at here. So V in T is Q2 V out, because when this switch is on, you're connecting V out to V in. And Q2 is Q1 minus Q1 right here, right? So that means whenever times your average time of switch 1 is on, that relays input and output voltage. So average input voltage over here would be 1 minus D1. So V out would be 1 over 1 minus D1 and V in, and current is opposite. All right. You can get the same. Equation by using energy conservation. Let me give you the equation here so you can do it by yourself. So if I do energy conservation for this circuit over here, let me draw the circuit over here again so you can have everything in one place. Right, so V out over here, right? And see, so this is the this is the switch number 2. Why are you doing that? Oh no, cannot let me do that. So this is the switch number 2. This is the switch number 1 here. All right. So this is the current going through IL inductor, and this is the V in over here. So now, if I do the energy conservation theory apply in inductor here, so 0 to dt, let's say d is the switching d ratio for switch 1. Again, in this analysis we're using d1 is d, and that will be VL IL dt plus dt to t. Now your VL again IL dt should be equal to 0. Inductor cannot store energy over a period. So VL, when switch 1 is on, VL over here, voltage over here, is V in minus V out. So 0 dt V in minus V out IL dt, right? And dt to t over here. Now switch 2 is on. Sorry, I made a mistake here. Sorry. I made a mistake here. This is, should be just when switch 1 is on, VL is V in because you're circulating in here, right? So and IL dt plus when switch 2 is on, then you have the loop. Oh, sorry. Now you have the loop from here to the output here. So you have V in minus V out IL dt, right? So equal to 0. So if you solve it, you'll also get the same equation here. V out, it would be V in 1 minus D. Again, D is D1, right? So that's for this boost converter relation in voltage and current. So, and again, we have a problem here. We're going to do it in the class. Come to class with the theoretical background, then we can spend time solving problem and understanding them better. And that's all. This is end of class 6. I'll see you all in class 7.